All right, what I want to do for this video is just shotgun through some of the part B and part B2 and part C, the short answer, where it's not multiple choice, and just if we can go through like 4 or 5 exams, hopefully we'll get a better feeling of what's coming on the test, which is tomorrow already. And I think most of these we've actually, in one form or another, gone over in class, because I don't want to go too far back in time. We want the more recent exams so that it's similar to what we're going to get tomorrow. So starting at this one here, number 51 on the diagram in your answer book, sketch at least 4 magnetic field lines around a bar magnet. This is the one I got so incredibly upset with because people weren't able to do this. And so with a magnet north and south, it's what a compass wants to do. A compass wants to point to the south, right? A compass wants to point to the south. So it's going to come, it's going to go away out here. Compass wants to point towards the south, which, remember, on the Earth, this is the Earth. What's north on a map is really the south end of a compass, and the north up here is the South Pole, right? Down here in this next one, this is modern atomic, and basically we're talking, this nucleus is composed of 1 proton and 2 neutrons. So I've got a proton with 3 quarks, and then I have neutrons, giving me a total of 9 quarks. What is the total charge in elementary charges of a proton, an electron, and an antineutrino? So what's going on here is when a neutron turns into a proton, it releases an electron and an antineutrino. So this is positive, this is negative, this has no charge. It started out with no charge, so the total charge is going to be 0. And what fundamental reaction is responsible for binding together the protons and neutrons? That's going to be the strong, right? And beta decay, which is what they're showing up here, beta decay is the weak force. But holding the protons and neutrons together, that's the strong force. And then holding the quarks together inside, that's also the strong force. So I'm not going to answer all of these, but I just want to kind of shotgun through some of these problems. Here we had a projectile motion problem. So again, projectile motion problems, usually we have to find the time, and usually it's d equals 1/2 at squared in the y direction. So we're going to make our chart, and we're going to remember that acceleration here is 0, and in the y direction, negative 9 meters per second squared. And then in the x direction, d in the x is always velocity in the x times time. This is shot out perfectly in the x direction. X is not changing. Here we're talking about a television set. So this is electricity. Well, I'm just going to have to deal with that, I guess. Television set, here's the amps, there's the voltage, and the time it takes to consume that many joules of energy, right? So you're just going to look on the sheet and realize that power is I times V. Power is also work over time, which is energy over time. And so I get energy over time equals IV. Again, all of that's on the reference table. Draw at least one periodic transverse wave with an amplitude of 2 centimeters and a wavelength. So most of you guys got this, but transverse wave, T, perpendicular, there's one cycle. And if it has to have a wavelength of 6 centimeters, that has to be 6. And if it has to have an amplitude of 2 centimeters, and that's 2. Or if you do it in meters, then you just have to correctly know that 6 centimeters is 0.06, right? And 2 centimeters is 0.02. It's 2 decimal places, so 0.02, 0.06. This is a Hooke's law problem, and so we need to know, right? If I get a spring, F is equal to Kx, where X in this case is going to be subtracting these two numbers. Of course, the other spring formula is 1/2 Kx squared. Don't forget that that's squared, and then this is energy. So if we're talking about energy in the spring, this formula. If we're talking about the force on the spring, it's this formula. Here I would subtract the two. If this is already in newtons, then that's the force. If they gave you a mass, however, you'd multiply it by 9.8. What else do we got going on? Determine the amount of matter in kilograms that must be converted to energy to yield 1 gigajoule. That's the E equals MC squared problem. Thunder results from the expansion of lightning. Everybody knew this, that speed of light is faster than the speed of sound. A bolt transfers this many coulombs of charge to an electrical potential of that many volts between the cloud and the ground in that many seconds. Calculate the average current between the cloud and the ground. Again, just all the electricity formulas here. And so one strategy is to, if you have the time, is to write down what you know. If you're running low on time, you can just circle it and say, okay, that's charge. And this here, that's time. And this here, this is voltage. And what am I looking for? I'm looking for current, right? Which is going to be I. I is Q over T, right? Something like this. And I think there was more than one way to get this answer. Here, right, this is wave interference. When these two come exactly together, 1, 2, 3, 4, 5 high, and this guy's -2, so he's going to be only 3. That's pretty simple. And we get to part C. I got a guy going up the ramp here. So, you know, a few things. It's going to keep doing this over and over. So, a couple of things going on. First of all, work is equal to force times distance. Work is also equal to the change in energy, right? Up here, we're talking about mgh at this point. While it's moving, although I don't think the question asks us this, he has 1/2 mv squared. And the work done by, the work's done by the rope is going to be the force of the rope times this distance, right? Force times distance. If I want to know the work done by gravity or what his potential energy is, then it's going to be, right, mg, the mass of this guy, times 9.8 times the height. So that's what we got going on there. Here we have a parallel circuit. So again, we spent a pretty good amount of time going over in circuits. 60 volts here means I'm going to also have 60 volts across here. I'm also going to have 60 volts across here. If I want the equivalent resistance, right, it's that reciprocal sum formula. However you practice doing it in your calculator, just double check your answer. The double check, remember, is that when you add them together, because they're in parallel, you're going to get a number that's smaller than 15, right? To find the current in the ammeter, I can find the current in each branch and add them. That's going to be the total current. Or I can say I is equal to V over R, where this is the total, right? Whatever that total comes out to be, and this is my 60 volts. So two ways in which you can do it. You could do it in each branch and add them together, or you could use the total resistance and use this. Calculate the rate at which the battery supplies energy to the circuit. I mean, again, you know, P is equal to IV, and so the rate at which, so the rate of energy is the power. And so for the whole circuit, I put in the total current, and then I would put in the 60 volts again. If another resistor were added, what effect would this have on the current through R1? Nothing. If I add another resistor, this guy's not changing. To the whole system, the current, total current, is going to go up. Just like in your house, turn on more lights, they're all in parallel. You're pulling more total current. Too much total current flips the breaker in the basement to prevent a fire. What else we got going on here? Airplane has that mass. Student exerts a force on the cord, keep it flying at a constant speed of that, and a circular path. And with that radius, calculate the kinetic energy moving in the plane, right? 1/2 mv squared, pretty simple. Centripetal force, it's just mv squared over r. Nothing going on there. And look, we have our friend Snell's law again. Refraction of light, Snell's law. What's going to happen? This is going to come in, and then, oh, in this case, the refracted ray is here. Because the refracted ray is 90, that automatically tells me that that's going to be the critical angle for this particular problem. And again, right, anytime you see this, n1 sine theta 1 equals n2 sine theta 2. Shouldn't have to say this, but make sure your calculator's in degrees. Calculator's always in degrees for everything on this test. We're not using radians for anything. Going to have to use your protractor, so make sure you know how to use the protractor properly. And that's it for that guy. So let's jump over to this guy here. Maybe we'll do 2 per video. So let's look at this one. 2 forces, 60 Newton force goes east, 80 Newton force goes north, act concurrently on point P. Use a ruler to determine the scale of the vector diagram. So, although I don't have the picture ready here, what's happening is that I've got, was this the one that was a boat? Anyways, I've got 80 going this way. Uh, 60 is going east. So I've got 60 going this way, right? So the resultant obviously is going to be somewhere in this direction. It's going to be more than 45 because 80 is bigger than 60. This, to find it mathematically, it's going to be this. To find the scale, you're going to measure how many centimeters that actually is, and then, you know, it's going to, and then you're going to get a ratio. How many centimeters, you know, or how many, really, probably you're better off doing how many newtons per centimeter, right? If it was 5 newtons for every 1 centimeter, then you can use that to draw vectors. Determine the magnitude of the resultant force, Pythagorean theorem. Determine the angle in degrees. So this is where you're, right, it's either going to be tangent -1 of the y value, 80 over 60, and this is inverse. You're going to use inverse on your calculator. Or you're going to do tip to tail, right? So you're going to remove that. You're going to move the 80 newtons over here, cross that one out so you don't get confused. And then you're gonna draw this guy in, right? You can measure him, use the scale that you just found, and then you can measure that angle. Or if you want to use math, or maybe you have to use math, it's going to be Pythagorean theorem and inverse tangent. So you will have to use a protractor. You will probably get a Snell's law problem. Here I've got a spring that's a force that's stretching a spring. It's going to be Hooke's law. Calculate the spring constant, right? So I mean, if F, so just like the lab we did, K is going to be equal to F over X. Calculate the average power required to lift 490 Newton object a vertical distance of 2 meters in 10 seconds. So, you know, for power, we have work over time, and work is force times distance over time. And so power can be thought of as force times velocity. And they're giving you this, it's already in newtons. And so we've got distance, we've got time, and we've got the force. So we're going to use this formula here. The answer in your, so then we have wavefronts approaching on there. The size, in the diagram and answer book, draw the shape of at least 3 of the wavefronts after they've passed through this opening. I don't remember what this one looks like, but if waves pass through an opening, they end up curving. So maybe it was something like that. Shows a mechanical transverse wave traveling to the right in a medium. Point A represents a particle in the mean drawn. So if I'm here and it's point A, he has to go up next because everything's moving this way, right? If I were to say, if point B was here, point B is going to go down next because everything's moving this way. Point A would be going up. All right, what else we got going on in this guy here? Explain why there's a difference between the total amount of energy provided by the source and the amount of electrical energy. What the hell is he talking about here? Draw an arrow originating at point A. All right. Regardless of the method used to generate electrical energy, the amount of energy provided by a source is always greater than the amount of electrical energy produced. Explain why there is a difference between the amount of energy produced and the amount of electrical energy. You know, I don't really think we talked about that, but basically that's talking about anytime you produce electricity, anytime you have energy transferring from one state to another, there's going to be energy lost to the environment, lost to heat, lost due to friction and sound and things like that. So I think that's what they're looking for there. Here we have this graph of velocity versus time. So before we even solve it, good God, you know, what types of things should come to mind with a velocity versus time graph? Well, let's see. If I have velocity versus time, the slope is going to be the acceleration, and the area under the curve is going to be the displacement. So determine the magnitude of the average velocity of the car from 6 to 10. So let's take a look. From 6 to 10, jeepers creepers, that's pretty easy. That's just going to be 15. What if they asked the exact same question, but they said the average from 1 to 6? Well, the average from 1 to 6 would be right in the middle, right? 0 to 15. So that's going to be like 7.5, right down the middle. Determine the magnitude of the car's acceleration during the first 6 seconds. Well, that's going to be the slope of this line. So since it goes through 0, 0, that makes that pretty easy. That's just going to be 15, whatever 15 divided by 6 is, right? So 2.5 meters per second squared. I'm just going to do the slope, right? Slope is y2 minus y1 over x2 minus x1. All the labs we did, you got to know that by now. And I'm putting in 0, 0 as one of the points. Identify the physical quantity represented by the shaded area in the graph. This shaded area here equals the displacement. So you would say the displacement or the distance that the object has traveled. What else we got going on in this one? Now we're on to part C. A student constructs a series circuit in the space plane. Draw a diagram of the series circuit. All right, that's going to be no problem. Determine the equivalent resistance of the circuit. In series resistors, just add. Determine the resistance. Well, let's see. A 12-volt battery, 10 ohm amp, and a resistor. The circuit doesn't, when operating, the total current passes. All right, so this one, you're going to have to work backwards. So to find the total resistance, you're going to say that the total voltage is the total current, right? We're going to deal with all the totals. Once you get what that total resistance is, you can subtract out the lamp here. Just moving on, because I don't want to waste too much time on details. Now we're talking about Pluto orbits the sun at that distance, and there's Pluto's diameter is that, and its mass is that. And then this moon orbits Pluto, their center is separated by that distance. Calculate the gravitational force. Come on, it's not hard. Just make sure you put the numbers into your calculator correctly. That's going to be F is equal to GMM over R squared. Make sure you have the right two masses. Calculate the acceleration of Charon towards Pluto, showing all work. So what is that going to be? F is equal to MA, and so A is going to be equal to F over M. I'm just wondering, is this a centripetal? No, so it can't be a centripetal force problem. So they're talking about this. State the reasons why the magnitude of the sun's gravitational force on Pluto is greater than the magnitude of the sun's gravitational force on Charon. Well, come on now, right? Pluto's this little tiny guy, and that's that guy. So it's because he has less mass, right? Pluto, well, here's the average distance, and here's its mass to the 22nd. This guy here is much closer, but it has a smaller mass. So again, it has to do with distance and mass. Well, this is orbiting. This isn't that mass. This distance here isn't to the sun, right? This is a distance. So the distance ends up being pretty similar to the sun, but Charon has much less mass, right? I know I stumbled my way through that, but you know what the hell's going on. Let's see. Horizontal force is applied to a box, push it across. So this is a friction problem, right? Friction force. I just did that video yesterday talking about friction forces. Just remember that if it's not moving, then the friction force has to be equal to the applied force. If it is moving, then force of friction is equal to mu times the normal force, and static would be if it is moving, then this is kinetic. If it's not moving, you put the static in, then that's going to be the max. Calculate the weight of the box. So in this case, we're working backwards, right? This one, I have the applied force, and I have the mass. No, we're not moving backwards. And I've got the speed here. So the weight of the box is just going to be mg. No, nothing crazy going on there. Let's look at this one. Electron traveling with this speed, having a frequency after the collision, the photon has this amount of energy, right? So this is where I've got some electron. It has some energy associated with it, right? 1/2 mv squared is its kinetic energy, and it collides with a photon. So now I got the photon coming in, right? That's E is equal to HF. after the collision, the photon has a different amount of energy associated with it. Calculate the original kinetic energy of the electron. So I can get the mass of the electron from the chart, and I've got the speed right here, so that's how I'm going to figure out the kinetic energy. Determine the energy in joules of the photon before the collision, that's going to be that formula. Determine the energy lost by the photon during the collision. Well, I'm just going to, it's telling you what it is, so I'm just going to subtract that guy out. Name two physical quantities conserved in the collision, and it's going to be energy and momentum are conserved. So maybe for the other ones I won't spend so much time solving them. We'll just talk about what the problems are, but there's 2 exams and just a feeling for what to expect.